Hey, John here. Let's talk about what it means to add and subtract binary numbers. For this, I'm going to be, again, referring back to this RISC-V Assembly Language Programming manuscript I'm kind of piecing together here. There's a draft on my GitHub page. There'll be a link to it below this video if you're on YouTube or a system that allows you to have links, or it'll be on my faculty page at NIU if you want to grab a copy of your own. Okay, so let's talk about adding. This is on page 13 of the current draft of this manuscript. Okay, so what does it mean to add two binary numbers? We already know how to count, right? So in theory, we already know how to kind of like add one. Let's go back to this table over here. Remember, we were talking about counting in binary and decimal and hex. And in order to count, you're really adding one, add one, add one. And we talked about that when you're adding 1 to 0 to get the value 1. It's easy. When you're adding 1 to the value of 1 in base 2, there is no value that represents 2. So you end up with 0 and a carry, right? Just like you do when you're adding 1 to 9 in decimal. There is no face value for 10. Therefore, you end up with 0 and a carry, all right? When you're dealing with a number base that's smaller than 10, you end up running out of digits more quickly. When you're in base 2, you run out almost right away, right? So you 0, 1, and then you got yourself a carry, and then you're back to 0, and you add 1, you get a 1 here, and then you're back to getting a carry, and you propagate the carries over just like we did in grade school. And when we learned how to add longhand, and that's kind of how we're going to do this in binary. When you want to add 1 or more than 1 to a binary number. So let's look at how that works, okay? How do you add binary numbers? Right now, we're talking about adding numbers that have no sign or an unsigned binary number, okay? Just to keep it simple, we'll add signedness later on as we go. So what are we going to do? We're going to do it long-handed, like I say here, and I point out that what you need to do in any number base is be able to add 0 plus 0 and get 0. 0 plus 1, and you need to get 1. And, of course, 1 plus 0 also gives you 1, right? Order doesn't matter with addition. It's associative. Now, there's no 2, just like I said, just like there's no 10 in decimal, right? If you go add in 1 and 1, I can't say it's 2. I got to have 0 and a carry, all right? Same thing happens if I want to add 1 plus 1 plus 1. There's no 3, but there is 1 with a carry, all right? Now, this might be easier to see if we put together a nice truth table. This is technically called a full adder. And we'll see a lot more about that when we talk about gates and other such things and how to actually build a machine that does addition, all right? And it's literally going to use this truth table to do the math. And this is our first real quantum leap, in my opinion. We've chosen binary because of this quantum leap right here. And there's other related ones, but this is the first one that I'm going to be discussing here in this series, okay? What is the quantum leap? Well, the quantum leap here is I'm going to do addition by only using Boolean algebra. I'm going to use logic to add things together. I'm not going to actually do math in a, sense that we learn in grade school. I'm going to only use logic, what we call zeroth order logic or propositional calculus, right? Boolean algebra. All those mean kind of basically the same thing, right? All right, so just as I describe in text up here, let's expand that out into a truth table, right? If I want to add 3 numbers. Now, the reason I'm adding 3 is because that's what we're going to have to do. Remember, when you add, you have to worry about carries. All right. So what you're really doing, we'll get that back down here in a minute, but bird's eye view here first. What we're going to do is we're going to add these two, what are technically called add-ends together. And while we're doing it, there could be a carry. So I need to be able to consider that I have to add 3 values together. Because you got to be able to add the add-end plus the add-end plus any carry that came in from a prior column. All right. Again, this is so intuitive. We don't really, maybe some of us don't really think about this that much. So let's put together a truth table that shows every possible way that you can add 3 binary face values together. Well, obviously, that's 2 to the 3rd power, total number of rows. We number them in order from 0 through 7 because that's the way you do a truth table, okay? And then we just show what happened. Well, what is the sum if I add all 3 zeros? Well, the sum is obviously 0. Did I get a carry if I'm going to add a bunch of zeros together like I did over here in the far left column when we get down here? No, there's no carry coming out of there. There's an in decimal either. So what happens if I get 0 plus 0 plus 0? I get a 1 for the sum. No problem. Is there a carry? No. Okay. What about 0 plus 1 plus 0? It's the same thing, but different combination. No, I get a 1 with a carry. No problem. What do I got? 0 plus 1 plus 1. Well, we already talked about that. That value in decimal would be a 2. We don't have a 2. So what we end up with is 0 with a carry. And if you think of these two, the carry out and this sum as a 2-bit binary value, look what we got here. 0, 0 is 0 in binary, is a 2-bit binary number. A 0, 1 is the value 1 in binary. 0, 1 is a 1. 1, 0 in binary is if you consider this a 2-bit binary number, is 2. All right? What if I add 1 plus 0 plus 0? Well, that's the same thing as adding 0 plus 0 plus 1, and the answer is 1, and there is no carry. Okay? 1 plus 0 plus 1 is really the same thing as 0 plus 1 plus 1, or 1 plus 1 plus 0. No big deal. You get 2, which is 0 with a carry. 1 plus 1 plus 0 is 2, which is 0 with a carry. 1 plus 1 plus 1 is 3. And in binary, 2-bit binary number, the number 3 looks like 2 1s together like this, right? It is a 1 sum with a carry, all right? So these are all the possible ways that you can add together 3 binary bits, okay? And again, we need to do 3 because we have to worry when we do longhand arithmetic like this, we have to worry about the carries coming in, all right? So let's say we want to do an actual addition like you did in grade school in 10 and base 10. I'll zoom in here a little bit. Maybe I get the truth table in here at the same time. That's good. Okay, what do you do? Well, this is after the fact. I'm showing the carries right here. So what we really want to do is add these two addends together, and we want to calculate this sum, okay? So what does it mean to do this? Well, you can just look all this stuff up in the truth table, or you can, think about it in your head and do the addition. 1 plus 1 is 0 with a carry, right? 1 plus 1 plus 1 is 1 with a carry. 1 plus 1 plus 0 is 0 with a carry. You can't remember. You go back and say 1 plus 1 plus 0, and you look it up in here. 1 plus 1 plus 0 is 0 with a carry, all right? So that was, we're adding this column right here, right? So you add these up and you get yourself a 0 and you have a carry. Now I got 1 plus 0 plus 0. You can look it up in this thingy here. That's 1 plus 0 is 1 with no carry, right? So there's your 1. And normally when you do this longhand, you just leave it blank here. But this carry coming out of here is 0, as is the carry, by the way, that comes in on the least significant bit here, all right? Kind of a special case. But in order to use this truth table to do this addition, you assume that the blank carries here are all zeros. And that's what you did in decimal. Anyway, you just didn't have to write them down. It's shorthand to leave it blank, right? So what do we got here? 0 carry plus 0 plus 1 is a 1 with no carry. 0 plus 1 plus 1 is 0 with a carry, and so on. You can just keep looking them up in here if you have to, or you can do them in your head, okay? As you do this a lot of times, you can just get better at it and remember what all these values are and go along, just like you do in decimal today, all right? Side note, all right? We've seen this before, haven't we? When we were talking about the Boolean functions, and I told you to think of exclusive OR not as what so many people do, and consider it for only 2 inputs and say that when the inputs are different, the output's true and so on. This is a 3-input exclusive OR function right here. So you can take a single operation, a 3-input exclusive OR, and use that to calculate the sum. Carryout's a little bit more weird. It's not immediately obvious what that is. Like we talked about in Boolean algebra, it doesn't matter how weird this is. If I can put it in a truth table, I can express this in the form of a sum of products. And I can also reduce it down, and it can boil all the way down to nothing more than a collection of AND functions, OR functions, and NOT functions. no matter what it is. If you can put it in a truth table, you can do that, all right? And we've just done this for here, so I can build a Boolean algebraic function that describes how to add one column, all right? And the truth table for that function is right here. And if I have many of those functions, I can have a function that does the first column, the function that does the second column, right? Function that does the third one, and so on. So we would say that I would use a full adder function for every single column of bits in this addition operation, all right? So that is our first real quantum leap. And at this point, you should be able to now see how I can add at least binary numbers together using nothing but logic. And because logic, as we will see, can be expressed using electronic gates, I can build an electronic machine that adds, okay, in binary. We'll talk about how to do it in binary. You can also do it in decimal and other ways. Obviously, Babbage did it in decimal using gear wheels and things, but those things ran rather slow. If you stick to binary, you can do things a little bit more quickly.